Hello, today I want to talk about the inputs data for crop modeling. They are very important because it's a very important information for run the model, and associated with that we need to follow some steps to build the experiment or found information to give to the model, make our simulation. Uh, Especially when you are calibrating the model, you need to be very clear what is the information that you need to make this calibration. So we are talking basic in three main inputs data that you need to modeling. That's climate and weather, soil, that you can use measurements or estimate data, and the field experiment, how you can build in this experiment, how you can measure these parameters or look for output to see if our model is simulating adequately the information that you need. So to start, we'll talk about a little bit about climate and weather. So the weather can be measured using this weather station here. Basically, these weather station measurements are air temperature, solar radiation, rainfall, wind speed, and relative air humidity. Most of the models need these five information. Sometimes I can estimate this or use other information, but most of model you're gonna need the air temperature, solar radiation, rainfall, and sometimes with speed and relative air humidity, dependent on the evapotranspiration method that you're gonna use. For example, in DSAT, I need all this information if I want to use the Penman's equation to estimate evapotranspiration. But if I use the Priestley-Taylor method, I need just air temperature, solar radiation, and rainfall. So I also need to look each are the minimum data that I need for my model. Based on this information, we also can calculate other variables like vapor pressure deficit or net solar radiation and others that I can use in my model. So here we have an example of one weather station. This is the location of the weather station here in the University of Goiás that use this data for field experiment. We also have some government institution in Brazil that organize this data and measure this data. We have these three men here. You can access their site and get information there for this. Another alternative use is use climate and weather data that were measured and processed to make some estimation. For example, we can use the grid data that these data are building based on the surface measurement using interpolation to create the weather data. So this paper show how they building this database to Brazil where we have data from 98 until 2014 or 15 or 13, depend on the year of the access. Here they work until 2013, but they make update recently that there are available data until 2017. We can access this information. So how work this grid data? Every one of these points are a weather station that make measurements in the field. So the authors of this work get these points and test different way to interpolate this weather data daily for all these regions. So here we have the weather station that have all weather data, and here we have weather station that measured only rainfall. So we have more weather station here measuring the rainfall in Brazil. So after that, they make some programming to interpolate this data from daily scale. So they use for each day from this period, they make interpolation to cover these areas where we don't have weather station. This create a big database where I can extract the data using this grid size uh, to get this data and make simulation. You use this type of data mostly for make long-term simulation. When I want to evaluate, for example, showing date, I can get this data from 1980 and make simulation to the present to see how is the probability of yield for different showing dates for the crop that I have interest. And here is the result for this work, where you can see for each square we have the weather data available. Here example of the 0.5 by 0.5 degree. So this is the size of the grid that you can use, but if you prefer, you can extract this data using 0.25 by 0.25. It's a very small grid size for climate study in agriculture. And based on this type of information, using this grid data, we make some evaluation. Here an example comparing the results for yield when you use this grid data from Agmira and this from Xavier, that is the previous database, where you compare how is the performance of the crop model using uh, weather data from weather station in the surface or using this data from grid weather data. Here you can see that for potential yield that include temperature and solar radiation, the performance for this grid data are very good, a strong correlation. For attainable yield, when you put rainfall in the simulation, you can see that you have some dispersion of the data, but most of the data are here in the line one by one. Okay, so we define the level of the error to use this data, and you saw that this error is acceptable for the proposal, especially to evaluate the showing dates and other managements for the crop. We have other approach that define the grid weather data using measurement weather station. Here is the example of this study where each one of these points are the available weather station in the road, and they use this weather station to calibrate the model to estimate the weather and use satellite information to extrapolate these results for other regions where you don't have weather station. So this is a very good database because they make some validation and adjustment in the model to cover better the region where I have more agriculture. So they make this adjustment to improve the performance over region with agriculture uses. So we can use also this database from this study that you can make simulation for any part of the world. Another database based in the satellite and was validate and calibrate, and there is data available from 1981 until the present, is this database from NASA. We call NASA Power. So this is the website where you define the latitude and longitude, define this location. You can put here, type here, or you can click in the map and he'll define the latitude and longitude for this point. And I can get this information, putting here the beginning, the end of the data, and choose each one of the climate variables I want to download. So here we have rainfall, wind speed, relative humidity, maximum and minimum air temperature, solar radiation, and mean temperature. So these are all the information that we need to make the model simulation. And here there is an example of this study that they run for Brazil, evaluate how is the performance between NASA power data and the weather station uh, data, comparing how is the performance to simulate sugarcane yield using this database. So also they also observe a good performance using this database for simulation. Another information that is very important for run the model is the soil. Most of the time when you make some big simulation like for a country or for the world, you need to access database that have all the information, and you can use some programming to get this data and put this in your model. However, when you look for a field experiment, you can measure this. Is more easy because it's just one point, but you can use both information to make the simulation. Thinking in a big way, we have here in Brazil this soil database that you call RADAN, where each one of these red points where is the point that was measured. So they make a hole and you get the soil from these 1-2 meters of depth. And based on this information, they have a lot of information that were measured. Here we have all the details that were measured, and most of the time what I do is to get the texture, silt, clay and total sand in this soil and apply this in a pedal transfer function to estimate the water available in the soil. So this is a very good database that you have available here in Brazil. We also have a soil map that define the type of soil. So you can use both information from RADAN and from IBGE, where you can get the type of the soil for the region that you are working, and based on this texture you can estimate the water available to the crop. So for example, when you get one site here, for example, I can define each type of soil I have here, and based on this type of soil, identify what is the texture or find some measurement in the region to use this data in my modeling process. In the same way, we have some initiatives that have building this soil database for international or national purpose. Here we have an example of the World Soil Information that brings soil details from any part of the world, and they building this platform that they call Soil Grids, that for using machine learning and all this database, they define for each point of the world what is the soil condition and soil information. So I can define here where I want to get the data, define here what is the depth that I want this data, what data I need for my proposal, and after this I can download this information and use in the crop model. So this is a very useful tool for any part of the world. What is the main point here is, if I have my data available from my experiment, I need to use this. If I don't have this information, I can get a texture, for example, and make some estimation using pedal transfer function to get the soil available to the crop and put this in the model. If I don't have this information, I can use this national or international database to define what is the soil condition in my experiment. So also always I need to look what is my M and each type of each level of information that I need to make the simulation or the calibration in the model. Here we have another example for a national database that is available in this website, where I have many soil samples in Brazil. If I make a click here and make a zoom, I can look specific for my region or my city. Each is the soil profile available for each location. The most of data from this database came from RADAN. That was the first example that I show here for you. But this database, in the most of time, they have just the texture or the soil type and don't bring information about the main data that we need for the model, that is soil water content at saturation, at field capacity, and in the permanent wilting point. This is very important for the crop because you define the soil water available and based on this information you can calculate what is the evapotranspiration, what was the water depth, and associated with this we also need sometimes the infiltration rate and the bulk density. Because this process here for soil water content, infiltration rate, and bulk density, it's I need to work a lot to make this information. It's expensive and it requires a lot of time to make this measurement. Most of the studies or the database don't have these measurements available. So one alternative is to get the soil texture or the soil type and use pedotransfer function that are simple models that estimate these 3 points based on the soil texture, for example, clay and silt associated with organic matter. Sometimes I need to include the bulk density or the type of the soil to estimate when I have the field capacity, one example here, and the permanent yielding point. So here we have example of the measurement of the soil water content, and here is estimate based on this equation here, calibrate for this state in Brazil. So I also can use this approach. Here another example for pedotransfer function specific for this region for center of Brazil, most of the savanna area, where they make some evaluation for different type of soil, and based on this information they building specific pedotransfer function for this region. So what is the approach? I can get this texture, soil texture from soil database and identify for that region each pedotransfer function is available, calibrate for that region, and using this equation to estimate the soil water content to put this information in the model. Okay, so you can see that always I need to make some measurements or and associated with this measurement I can use equation or another simple model to put the real value in the model, and based on this making my simulation. What's important to highlight here is that always that I use an equation to estimate some parameter or some input data, always I have an error associated with this estimation. So there is some studies that evaluate if I am getting wrong 10% of the soil capacity, what's gonna happen in the final yield. So you can make this simulation to evaluate how is the error in my model based on this characteristic. Okay. After we have soil and weather data, we need to make some measurements to define the calibration in the model using field experiment. In the previous class, I bring some example how to obtain this data, the parameters, and how to measure some things. But here we are looking specific for field experiment, what I need to look to building my experiment to get the right parameter or the output. The first point that I need to look for field experiment, looking for data for calibrating the model, is that this experiment need to follow the experimental and the statistical principle. So I need to look for the replication, I need to look for the size of the sample. So I need to reduce the error from the experiment field to the maximum that I can. And to reduce this error from experiment, I need to look for the size of the plot, how many sample I need to get to represent that crop. So all this information needs to be very well defined to avoid errors in the measurements that wanna lead the model to a wrong simulation. Okay, so this is the first point that you need to look. The second point, the measurement data need to include variability. So when I look for a model, my model needs to represent different conditions of growing crop, including siting, showing dates, irrigation, fertilization, soil type, cultivars. Uh, I need to bring this variability to my model to test if the equation, if the parameters that I am using in the model are good enough to represent when I have a variation, for example, of the available water to the crop. I need to test my model in these different conditions. And here we have an example from experiment that you have a good range of yields. I have 1,000 to near 5,000 tons per hectare in the same plot in the experiment where the showing dates and irrigation and sites are affecting this yield. This variability put my model in different conditions that it need to be simulated. So if my model are being calibrated under a condition with water stress and no water stress, I can calibrate better my model, adjust better the parameters that I need to calibrate and get a good result. And this makes my model able to be applied for other region under the same condition. For example, with water depth or no water depth in the simulation. A third point that you need to look is the verify the requirements from the crop models. So sometimes I make experiment, make some measurements, and don't look what is the definition in the model for the parameters or each type of measurement I need to make the calibration in the model. Here we have example for three models, DSAT, APSIN, and Monica, where in the model we have the state variables, the leaf area index. So if I'm gonna work with these three models, I need to measure leaf area index in the field. This is a requirement. However, in the aquacrop, the model uses a different approach that the model don't use the leaf area index. So for this model, I don't need to measure leaf area index, but I need to measure green canopy cover that represent how many percentage of the soil is covered by green leaf. So it's a different parameter from these two. So I need to look this and in my experiment to measure these different parameters that is a requirement from the model with a different definition of leaf area index. In this case, in my experiment, what I did was to measure green canopy cover and measure leaf area index. And after that, I create a equation where I represent the green canopy cover based on the leaf area index. So if I have one experiment where I didn't measure this green canopy cover, I can use this function to estimate the green canopy cover based on the leaf area index. And here is another example of the importance of the definition. For example, here is the parameter in DSAT where this parameter represents the time between first flower and the first put. And here also first flower and the end of the liquid expansion. In the most of time in the experiment, we make a measurement following the Fehr and Kavinsky phases defined in this study for soybean. But in the most of the models that work with soybean, the definition is different. So I can use, but to improve my efficiency, I need to measure this specific crop phase, first flower and first put, not the definition of other phenological scales, because I can create an error inside of the model because this type of measurement in the system. Another point is we are working with different type of models, but when you are working with a mechanistic model, I need to validate the intermediate process. For example, I want to look for yield. Here is an example. In this study, we measure grain yield for different cultivars and simulated this for different experiments. Here you have yield. So we have a line one by one, and you have this point around here, this line showing the good efficiency of the model. But in this case, we use the DSAT model that have a main of process being simulated until arrive in the yield. So when you see this cultivar, you see that the results are very good, a low error for calibration and evaluation. But when you look here for this cultivar, calibration was good, the blue points here, while for the evaluation, we saw the model over predicting this yield. So I can follow up and accept that this error is correct or it's acceptable error for my simulation, or I can look for another variables. For example, for this cultivar, we have a leaf area index for this difference point here. You can see this result, but I want to show is this here. We can see that these 4 points for evaluation, they represent a higher error than the others. And when you look at the leaf area index for these 4 points, you can see that the error, especially for these points with a higher leaf area index, the error in the leaf area index was higher than for the other points. So the explanation for these 3 points here, 4 points, have a high error was something in the leaf area index that the model not predict very well. So identify these, I can come back in the data, look for the calibration for leaf area index and see if I can make this simulation. Getting right the leaf area index, I can get right the yield. So the leaf area index is a intermediate process that need to be validated and calibrate well to get the right result. And you also can use the experiment to define specific parameters in the model. Here example how you can define the development rate based on temperature. Define here the points for cardinal temperature. Remember that we showed previously that we can build in this curve to represent the crop development, and using experiment we can look here for what was the mean temperature during each crop phase and calculate here this relative development rate that is based on the time from start to the end of the crop phase in a relative way based in the longer period that the crop expand to building the cycle wall or the specific phase that you are looking. After that, we can get this different point and building the curve that we need. How to building this curve? I can have different environmental with temperature control, like in a chamber, and control this and define this temperature points. Or I can use different site and showing dates that create a different air temperature for the crop, change the cycle response in function of the temperature. And after define these 4 points, we can make the simulation of the thermal time for the crop complete each one of the phase that we are simulating in the model. Okay, and so that we don't have measurements here in the extreme point, but you can use this approach of continue the same rate to define the minimum and the maximum temperature for the crop. Another example is the radiation use efficiency. Here is an experiment where the research evaluates different plant densities for maize with different irrigation condition and different system of planting with cover crop and without cover crop. And based on this information, they get this different rate where I have here the photosynthetic solar radiation, and here I have the biomass accumulate across the cycle. In this upper line here is the irrigation condition, and here is the rainfall condition in the model. So I can use this data to calibrate the radiation use efficiency, or I can build a model based in this rate calculated here by this experiment. I need to look carefully how is the definition of radiation use efficiency in the model that I am using to define what's the best approach. To use this biomass to calibrate the value or use these defined parameters in this equation here as a real value for radiation use efficiency in my model. And the last point, uh, one example of how you can calibrate the response to water depth. So I can create an environment with different water level available to the crop, here based in this function and the fraction of transpirable soil water, and how is the relative transpiration rate. So how much is a crop in a better condition with no water stress, how much the crop is transpirating, relate with another crop with different level of the water available to the crop. So here you can see in this example that when you have the soil in the field capacity have the maximum, and when the soil water content start to reduce, the crop keeping the maximum transpiration, but when the crop reach this point here, around of 0.36, the transpiration is reduced because the crop start to close stomatal and reduce the transpiration to save water and avoid the water loss, but consequently I have a reduction of the transpiration and the photosynthesis by the crop. So based on this experiment that can build in a field or in a chamber or with using pot to make this change in the soil water available, I can make it this plot and define how is the crop response to water depth. So in this class you saw that we have different alternatives to get these inputs, and always I need to look to the error associated with this information and to define if this information is good enough for my model, if the error associated with this estimation or this database can be minimized in my simulation. Okay,